Welcome. We're going to move into chapter 9, which is about counting and probability. Counting is often known as combinatorics. That's enumerative combinatorics is the fancy term that we have for counting. It's a major part of discrete mathematics. And probability we're going to deal with is actually what's called discrete probability. We're not going to get too much into general probability. This is not a stats class. We're not going to do normal distributions and so forth. In fact, actually, this normally fits more of, we can talk about different distributions of binomial versus normal versus Poisson and all these other things. That's a whole different ballgame. We're not going to go there. But we are going to do the basics of what is probability because this is a concept that's going to run throughout computer science. Whether you are doing data analysis and you haven't used some probability and need to understand that, though that usually requires a little bit more statistics, or more importantly, if I'm doing an analysis of something and trying to determine what's the likelihood of someone guessing something, especially in cryptography, this is a really important idea. If I'm running an algorithm, what's the likelihood of it finding the right value, all these different things. So let's just talk about the basics of probability. So let's start with a coin. If I'm flipping two coins, obviously the probability, the options that I can come out with are I can have zero heads, one head, or two heads. And so this is a way to kind of guess that these events occur one third because there's three options. We'd often say there's three of them. However, if I flip the coin 50 times, as you can kind of see looking here at this table, these numbers don't seem about 50. Like this one, middle one seems about 50, and these seem actually more like a quarter of the time. Why is that? And so what it turns out is because there's actually some things that are part of this whole process. So one of the ways that sometimes we do, and this we have some numbers here. We have a tally, and this is called frequency, i.e., the tally, how many tallies. So how many times did it occur? And then frequency is the percentage of times that occurred. Because we would expect this to be a third, which is about 33%. That's not 33%. Looking at this doesn't look the way we expect. Why? Well, we can get to that a little bit later. So let's just understand a little more about probability. When we analyze probability, it extends to a lot of things, and we're going to talk about what are known as random. Random means each outcome, process when it takes one outcome from a whole set, and it's impossible to detect with certainty what that outcome will be. In other words, let's say I'm picking a number from 0 to 10. If each number has an equal likelihood of being picked, we call that random. However, if there's a bias that me that I love to pick even numbers, then it's no longer random because now you know something about me and you know the way that I'm going to pick, and that's going to affect things. So let's do a different example to illustrate this. For example, if an ordinary person performs the experiment of tossing a coin in the air and allowing it to fall to the ground, it can be predicted that it'll land either heads up or tails up. So our outcomes are heads or tails, and it will not know for sure whether heads or tails will occur. This is why people are just guessing when they do this at sports games all the time. How do I make a decision? Let's flip a head, let's flip a coin. Because if it's truly random, then there's no way for that to come out and know it ahead of time. Now, when we restrict this experiment to ordinary people, because a magician might know how to toss a coin a special way, a physicist might have first-rate measuring devices that can analyze all the forces and predict the landing position. Obviously, we're talking about real world people because, again, the truth is there are things that do affect flipping coins. It's not entirely random, by the way. People have talked about this. I think I saw a video a few years ago from Mythbusters where they actually did this with toast. They flipped toast, butter side, non-butter side. And if they did not push in with the butter, it really had a 50-50 outcome. However, they pushed in with the butter, they then created a dent that affected the physics of the process and so forth. So we're just going to assume that normal people, because this random process is things like how do you pick the lottery values? How do you pick if I walk in to respond to something and I don't know anything better, that's random. So we assume randomness and then we move from there because randomness is the thing that's easy to guess. And then we can see if there's bias or something else affecting it. So let's just talk about some key words here. The first one is sample space. That's a set of all the possible outcomes that I can get in something. And an event is a specific moment in that sample space. So to go back a few slides, here, my sample space was I got zeros, ones, or twos. This right here was all my possible values. And each one of those was a very, very specific event in that. So sample space is all the possible events, and an event is a specific moment there. All right, so probability comes out to this, and this is the general formula for probability. If we're going to talk about probability, that's the majority of chapter 9. It comes down to this idea. Probability is the number of outcomes in an event divided by the number of outcomes in any given event. So let's say an event is, let's say I have 2 kids. How many ways can I have one boy and one girl out of 2 kids? Well, that could have been a boy, boy, girl, or girl, boy. Wow, I cannot say that. So I apologize. Those are both, but what's the total number of ways I could have had kids? I could have had a boy, 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 girl, girl, boy, girl, girl. So those are my different options. And I'm not trying to do any gender things. I'm just trying to explain genetically how we kind of project these sort of things. So we're trying to count how many things are in each of these, and that gives us the probability formula. Another way to think about that is the number of elements in the element set. And I really don't like this where your book has this N of A. That really notation is really, really poor, and not honestly not common. More common is actually the notation. Let me change my color real quick. So often we actually write this when it's talking about cardinalities of a set. This is the terminology we use. We use vertical lines. Again, the N doesn't really make sense because there's a lot of different N functions. You could have a null function, a lot of other things. So your book uses this, and I'm showing it to you because your book does it, and that's not fair if you don't know what your book says. It really isn't common. I don't know any other book that does it. All the rest of them use those vertical lines to indicate the count of a set. All right, so let's just talk about some examples of this. Suppose I have an ordinary deck of cards. We're going to do a lot of things, by the way, that deal with cards, deal with dice, and so forth, just because we're going to deal with some very, very simple things. There are 52 cards. There's 4 suits, namely, there's diamonds and hearts, clubs, and spades. The red ones are diamonds and hearts. The black ones are clubs and spades, if you don't already know that. Each suit has 13 cards. In the following, it calls them denominations. I call them values. And 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, Ace. And often we call the Jack, King, Queen face cards, because they actually have faces on them. The Ace, again, we're not putting a value, we're just calling a number here. Sometimes people consider Ace low, Ace high. There's a lot of different card games, but we're just going with what's likely of things happening. So an interesting the mathematician Percy Diaconis worked with David Aldous and David Beyer to show that 7 shuffles are needed to thoroughly mix up cards in an ordinary deck. Meaning, in order to mix this up, I have to do it at least 7 shuffles. So, and this is something that is known. I've played cards my whole life, and this is something. And in 2000, this was again worked on by Nick Treffelin and his father, who's a mechanical engineer, to show that 6 shuffles is pretty darn close. 7 will guarantee there's a certain values of randomness that we get to. So let's talk about some deck of cards and some different probabilities. Let's assume our deck has been thoroughly mixed up by whatever method. And let's talk about it. What is the sample space of outcomes? So we're going to pick one card face down. So the outcome, the sample space is all 52 cards in the deck. So if I'm pull a card out, so again, how likely are you to get any one card as another card? So each card, I'm going to have 52 possible cards I can pull out. What is the event that a chosen card is a black face card? That means it's a black card and it's a face card. Well, remember, each suit has 3 face cards, namely Jack, King, Queen. Also, in addition to that, we have 2 black suits, clubs and spades. So we have actually 6 of them in total, with the Jack, Queen, King of clubs, and then the Jack, King, Queen of spades. So we have 6 different events in here that correspond to a black face card being drawn. Last, once a probability of black face card is drawn. Well, that is this part B, which was 6 different options out of the total space, which was 52. So we're going to get 6 divided by 52, which is about 11.5%. Again, if you want to leave it at 6 over 52 on like tests and things like that, I'm not going to slam you really hard because you don't have a calculator. The idea is to set it up, not to worry about the computation. The one thing I will note is that you should recognize this number right here is less than 1. All probability is between 0 and 1. That is because it is going back to the very definition, it is a fraction. And the top is an event, but the events come from the space in which we're working in, which means the numerator can never be bigger. If you ever come with values and the numerator is bigger than the denominator, then you have done your probability wrong. Similarly, I can never have a negative value. So it's always going to be between 0 and 1. 0 means it's never possible. 1 means it is always and completely possible. Not just possible, it will happen that every single time. It's guaranteed. We all like a probability of 1, especially if it means like winning the lottery. But unfortunately, very few things in this life have a probability of 1 short of, as the saying goes, only 2 things in life are guaranteed: death and taxes. All right, so that's this. So let's get back to counting elements because that's a big part of it. So remember, if we're going to be counting things, how many are there? Then this gets to the idea of how many do I have in a list? So our first question is, let's just take a list of things, and we're going to do more counting things as we get on in the future sections. But suppose I have the elements of a list. So let's give you a simple example. We're going to start really simple for counting. How many integers do I have from 5 all the way up to 12, including the ends, inclusive? Well, if you assign 5 as 1, 6 as 2, 7 as 3, and so forth, you can notice you have 8 of them. It's really easy. I think many of us would probably even do something like 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's great. That's great for this. What if I give you a much bigger list? None of us want to be there counting something that has over 100 elements in it. So how do we do this more efficiently? Well, to get a more efficient formula, a way to think about it is this. So let's just pick any 2 integers, m and n, and let's just assume that n is at least as big as m. So they're either equal or n is bigger, right? Because m is where we're starting and we're going to n. So we're always going to start from smallest and go to biggest. Well, where did I get this equation right here? Well, just to quickly show you, we can all see that n minus m equals, well, n minus m. They're obviously equal. If you add m to both sides, then I get m plus n minus m. And these will cancel out and just give you n over on this side. So that is how we get this thing right here, which again is assuming that n minus m is bigger than 0. So we're okay. So wait, what does that mean? And this is where this next paragraph is kind of important. If many people are saying, so if I ask for all the numbers from 5 to 10, many people look at this and say, okay, that's 10 minus 5, it's 5. But if you actually have them 5, 6, 7, 8, 9, 10, it's because this right here is that difference. So this is n minus m, but that doesn't count the very first element in the list. So we have to actually take n minus m plus 1 more. because we have to add in that very first term to make this make more sense. So this, our very first theorem of combinatorics, seems like a relatively simple one, but it's that if m and n are integers and m is less than or equal to n, so n is at least as big as m, then the number of integers from m to n is n minus m plus 1. Was that really confusing? It sounded confusing in my head. But the idea here simply being that we are counting all of these values over and over and over again. All right, so let's do some examples, maybe to get this illustrated a little better in your head and help you understand this idea. So how many three-digit integers from 100 to 99, inclusive, that means including the ends, are divisible by 5? We'll come back to the second question. But how do I do that? I mean, I could count how many three-digit integers there are. That's really easy. But just saying, when I just say three-digit integers, again, that means obviously the smallest three-digit integer is 100, and the biggest is 999. So one of the ways I can do this, I can just start making lists. And notice 100 is 5 times 20. 105 is 5 times 21. 5 times 22, and so forth. Well, notice these are 5 times other things, starting at 20, going all the way up to 99. So because we can see that right here, my values that I'm multiplying the 5 by are actually going up, because I'm just highlighting the ones that I'm going to want to pick, then this question that I had was really the same as asking, how many integers are there that go from 20 to 99? Okay, can you pause the video and figure out that answer? All right, so hopefully you did do that. And again, this is just going to be 99 minus 20 plus 1, or 180 digits. So there's 180 digits from 100 to 99 that were divisible by 5. And that is really, really cool and powerful thing. There's a couple other ways to approach this problem and done it that are completely different. One is to say, how many numbers are there from 1 to 1,000 that are divisible by 5? Well, if I do that one, that's a little bit more complicated but it still works. If I go from all the numbers 1 to 1,000, and then I say divisible by 5, well, that's 1,000 of them, but only every fifth one is going to qualify, starting the fifth one, because 5 is the first one. So that would be 1,000 divided by 200, or in other words, divided by 5, which is 200. Let me get rid of this. 5. But notice, but we're not going to have, but 1,000 is divisible by 5. So we can minus 1, which gets us over to 199, right? But notice, I'm going to again do something else. From 1 to 100, that's divisible by 5, is going to be 100 divided by 5, which is 20. Oh, but we want to include the 100, but we don't, and this one's excluding. So if I took 199 minus 20, I'd be taking away all of these values, including 100. So again, we add that one back in, which is almost like counting this thing, and we end up at the 180. All right. I'm just trying to show you there's multiple ways to attack these problems, and none of them are wrong. And that's a key thing in combinatorics. There's often many ways to attack a problem. So let's go back. The other question is, what's the probability that a random digit is divisible by 5? So we're going to pick. So how many total digits do I have? Well, if I do 999 minus 100 plus 1, there's 900 digits. They're possible. That's integers. So that should make sense. And since I have 180 before, I just set that up as 180 divided by 900, which is 1/5, or about 20% probability. So if you give me a three-digit number and ask me what's the likelihood that it's divisible by 5, it turns out that is equal to 1/5. All right, so this is a very simplistic example. I know it's not super complex with any crazy formulas. It's getting to think that how combinatorics works. So we're trying to find different ways to look at these things and to have a general way rather than trying to brute force our way through these processes because honestly, we get to work with much larger numbers and brute force really sucks and in fact doesn't really work. And we're trying to find the general patterns to describe those and utilize them. So let's apply this actually one other way. Suppose I want to actually count some kind of computer algorithm. Now, for those you don't know, an array, one-dimensional A with n integers. Sometimes we do the algorithm. It starts with A1 and goes up to AN. That's not index 1 to index n. This also could have started at index 0 and gone to index n minus 1. Same exact idea. How many elements do I have in my array? So this is a stub array where notice I have A1 to M and then AM plus 1 all the way up to N. So how many elements are in each of these? Well, the first one should be kind of obvious. This one has M elements. Well, this one is really the same thing as the whole array, just minus this M. So that would be N minus M. So I can just take those away. All right, so that's our first question. How many elements are in those? And if we go through it, it's pretty simple that there are M elements to the first part in array 2, which has AM plus 1, from M plus 1 to N. Do the calculations, you get N minus M. So notice this value, the number of elements in the list, is already something we've already talked about. We've already calculated. We have this. Second question, though, is what's the probability that a random element has an even subscript? In other words, what's the probability it's even? Well, it turns out that if n is even, we end up with a subscript of 2, but it kind of depends on if n is even. And then we have n over 2 divided by n, which is just, well, 1/2. Because if we're dealing with even integers, then half of them would be true. But what if n is odd? Well, then the number right below it, n minus 1, would be even. And so again, we actually can do this calculation. We just get n minus 1. So we end up with n minus 1 over 2n. And this leaves us with an interesting problem. Like, how do we deal with this to figure out? And this actually is where we get what's known as the floor function, which is often called round down. So we have n over 2 round down, which means if n is even, it's just what it is. And n minus 1 divided by 2 if n is odd. Now, to further illustrate this floor function for you, because it's actually a super valuable function in computer science and discrete mathematics, if I took the floor function of 3.9, it's a rounding function, but it automatically is just going to give me the next integer down, not the next integer up. So we're going to use that and leverage it and kind of work our way through these different ideas. Just know this is going to come up over and over again. But if any of you are ever working on algorithms, this is something that actually comes up as how many elements do you have in your list? All right, let me know what questions you have.